Now we know a lot about histogram shapes and about their centers. However, what about their variability? Some histograms are going to be very wide, some histograms are going to be very narrow. Now, understanding the variability of these histograms is going to unlock probabilistic modeling. So let's get diving into it and let's have a look at how we measure the variance or the variability of our data. So now we know a lot about histogram shapes and about their centers. However, what about their variability? Some histograms are going to be very wide, some histograms are going to be very narrow. Now, understanding the variability of these histograms is going to unlock probabilistic modeling. So let's get diving into it and let's have a look at how we measure the variance or the variability of our data when displayed in our histograms. Now, like the average measurement that we call the mean is great and it's appropriate for symmetrical distributions, very good for taking in all that information and giving us the center. We also have a measurement of measuring the variability, which conveniently is called variance. Now, if you think that the criteria of looking at symmetric distributions moving forwards is a little bit overly restrictive, fear not, because we will be exploring some rudimentary transformation information a little bit later on. But for the moment, this is what we're going to be focusing on. We're going to be focusing on the symmetrical distribution with a mean as a measurement of mean of our center and our variance. Now, how do we measure variance? If we have the mean of a distribution and we try to sum up all the different variations of the distance between the data points and the center on the positive and negative side and put them all together, the average result is 0 because of course we're measuring everything to 0 and there's as much positive variation as there is negative variation. Obviously, this isn't going to work. So we have to use some mathematical trickery in order to make it work. So the mathematical trickery that we use in order to solve this problem is by actually squaring everything. If you square all the different measurements away from the center of the distribution, what this actually does is convert all of these variations into a positive number. Regardless of whether they're on the positive side or the negative side of the distribution, they're all going to result in positive numbers. This means you can look at the average variation and all the squared numbers are going to be positive numbers, which means you're going to get an actual real result. The average of all of these squared measurements is called the variance. Now, if you're thinking to yourself, but Adam, doesn't squaring all the variations fuck up the measurements? They're all going to be exponentially larger than they ought to be. And you would be correct. We fix this using some more mathematical trickery by taking the square root of the variance, which gives us the standard deviation. The standard deviation is the holy grail of measurements of variation. It is a magical ruler which allows us to unlock the secrets of the universe when it comes to probabilistic measurements. The standard deviation is so important that what we're going to do is we're going to cover it with a couple of different examples. Probably the easiest example of something that I can show you when it comes to standard deviation and how we use that to determine our measurements is with a real life example that makes sense to most people. For example, heart rate. If we have a whole bunch of people sitting in the room, hundreds and hundreds of people sitting in a room, and we take a histogram of all the different heart rate measurements, we're going to find that the average or the mean resting heart rate of most of the people in the room might be, say, 70 beats per minute. But of course, we know there's going to be some variation to this. The question is, how much average variation are we going to have in these heart rates? So if you know that within a room, the average is 70 beats per minute, and that the standard deviation is about 10 beats per minute, this means that you know that the majority of the people in that room will have an average heart rate of somewhere between 60 to 80 beats per minute, and this will encapsulate most of the people. This is because we already derived these measurements from the averages and the amount of variability. Remember, we took the mean, then we had the amount of variation, we squared all the different variations, and then we took the square root of that, which gave us the standard deviation. Now, of course, you have more variation past one standard deviation, but we'll cover this a little bit later on. Just know for the moment that the standard deviation encapsulates the average amount of variation away from the average. So 70 beats per minute is the average of everybody, however 60 to 80 encapsulates the majority of the variability. Now, what can go wrong with measuring a whole bunch of different measurements? Now, I just want to cover a fundamental principle here, and that's in Clown World, a lot of bad information is given to people. This can come in the form of stationary means being used on trending data sets, or maybe it's information that hasn't been adjusted for another measurement. For example, economic numbers. This type of shit happens all the time where you have, say, $1 million of economic activity was generated, and it's like, well, cool. $1 million of activity, but is that big or small relative to the country? But also, of course, this leads back into the main point, which is one of the worst possible things is to be given an average of a data set with no information on the variability. If you have an average of a data set and you don't know what the variation is, the variation could be super wide, or it could be very accurate and very narrow. We want, if we're going super precise and we're doing some sort of modeling, preferably we want the standard deviation of our errors to be as low as possible. This means precision. and, a wide range of different outcomes on a different type of data analysis. I can't think of one right now, but in different circumstances, maybe a wide standard deviation isn't so bad. It's not necessarily good or bad per se, having a wide or a narrow standard deviation, just as long as you know how to measure it. And as we move forward, we'll be looking at different ways that we can use the standard deviation as a powerful ruler and as an error detection system as well. The reason why not including standard deviation with averages is a problem is for a basic example I can give to you right now. Imagine that there's 100 people in a room and the average heart rate is 70 beats per minute. This is fantastic if the standard deviation is fucking 0. However, if the standard deviation is 100, you're going to have a whole bunch of people who are dead with a heart rate of 0 and a whole bunch of people in cardiac arrest with a heart rate of 160. The moral of the story is that standard deviation matters. Also, pay attention to outliers on one side. If it's symmetric and you have outliers on both sides, that's not such a problem. But if you've got outliers on just one side, that's going to fuck up your standard deviation. Because remember, like the mean, standard deviation is not resistant to outliers because it uses the mean as one of its inputs. Now let's look at a practical example of measuring standard deviation in something that we can all relate to, which is the price of Bitcoin. Let's measure its average variation over one day. If you look on the screen, you can see a familiar chart. This is the same one-day histogram of Bitcoin returns over one day from the previous examples. We also have a couple of different indicators on TradingView. You can see that the standard deviation of Bitcoin daily changes is about 6.7%. I did this the cheat way, which is using a bunch of TradingView indicators built on top of each other. And if you look at the histogram, you can see 6.7 is approximately where one standard deviation should be on that histogram. So this is a great example of showing you how you can measure the average variability of price, for example. So in summary, now we know from our previous lectures how to take an average measurement of the center of a series of data. Now we know how to take a measurement of the average variability of a series of data using the standard deviation as our magical ruler. The standard deviation as a measurement is a means of unlocking the magical tactical nuclear warhead probabilities of statistical analysis that we all want to get. This is one of the most foundational principles and is one of the most important measurements in all of statistics. Knowing how to calculate this can potentially really help. If you want to do extra research, if you want to do extra study on this, I would recommend understanding how the standard deviation is calculated will be very beneficial for you moving forwards. However, if you just understand it conceptually, we can expand on this in some more lectures that I have coming up, and it will make more sense over time. So it's only optional. Hopefully, I'll be able to explain it all to you in a clear manner so that you can see how we can apply this practically when it comes to data analysis. I'll see you in the next one.